Brad Williams, Frugal Finance, the Black model. In addition to options embedded in debt instruments, a number of different types of freestanding interest rate options exist, and these can be valued directly. This section explores the Black model, which serves as an industry benchmark for the evaluation of many types of interest rate options. As we will see, it is a direct extension of the Black-Scholes model. We introduced Merton's extension of the Black model that looks at options on stocks paying a dividend at a continuous rate. There's a third player in this, and it's Merton. Let's introduce a little variety here. Let's look at a couple of different examples. In addition to calculating theoretical prices for mortgage-backed securities and other bonds with embedded options, traders also like to compute what is known as the option-adjusted spread. This is the measure of the spread over the yields on government treasury bonds provided by the instrument when all options have been taken into account. All inputs to any term structure model is the initial zero coupon yield curve. Usually this is the SOFR zero curve. However, to calculate an OAS for an instrument, it is first priced using the zero coupon government treasury curve. The price of the instrument given by the model is compared to the price in the market. A series of iterations is then used to determine the parallel shift to the imputed treasury curve that causes the model price to be equal to the market price. This parallel shift is the OAS. To illustrate the nature of the calculation, suppose that the market price is 102 and that the price calculated using the treasury curve is 103.27. As a first trial, we might choose to try a 60 basis point parallel shift to the treasury zero curve. Suppose that this gives a price of 101.20 for the instrument. That is less than the market price of 102. It means that a parallel shift that is less than the market price of 102 and means that a parallel shift somewhere between 0 and 60 basis points will lead to the model price being equal to the market price. We can use linear interpolation to calculate 60 times 103.27 minus 102 divided by 103 minus 101 equals 36.81, or 36.81 basis points as the next trial shift. Suppose that this gives a price of 101.95. This indicates that the OAS is slightly less than 36.81 basis point. Linear interpolation suggests that the next trial shift be 36.81 times 103.27 minus 102 divided by 103.37 equals 35.41, or 35.41 basis points, and so on. The Merton model equation, we're looking at a call price, equation 19.4, DISA 1, log normal, similar with a few variations to account for, well, I'll tell you here in a second, where this symbol is the continuous dividend rate on the stock. So that's what we're solving for. Previously, we noted that Fisher-Black extends the Black-Scholes-Merton model to options on future contracts. The rate at which the spot price grows, R, takes the place of delta, and the future price takes the price of the stock price in Merton's model. In other words, for futures on commodities that conform to the cost to carry model, continuous dividend rate is equal to R. When we make this substitution in equation 19.4, the formula becomes considerably simpler due to the equivalence of continuous dividend rate and R. For European future options, the price of the future call and put are given by the Black model. Black model equation, C, EXP, etc. But then you have P, PF, DISA 1, and DISA 2. Equation 19.5 employs the standard deviation of the future price. If we compare the Merton model and the Black model carefully, we can see that there are only two differences. The first difference is that the future price, F of T, takes the place of the stock price. The second difference concerns the interest rate. We consider each difference in turn. Futures and forward prices are not necessarily identical. Differences in the two prices are due to varying interest rate patterns and their effect on the daily settlement cash flows of futures. These differences tend to be statistically significant, but economically small. In the Black model, the future price appears as a proxy for the forward price of the goods at the expiration date of the futures. This is tantamount to assuming one of two things. First, it may be regarded as assuming that interest rates are non-stochastic, so that differences between the futures price and the forward price is not economically significant. That the future price is a good proxy for the forward price. In practical terms, the assumptions are not onerous. The Black model works extremely well for many interest rate options. The Black model, as developed and as specified above, pertains specifically to options on futures. However, because the future price is being interpreted as a forward price, the model price of a bond could take the role of F in the Black model. When the terminal price of the underlying good at the expiration of the option is distributed log normally, the Black model applies. We will consider a variety of applications and extensions of the Black model because the good underlying a futures contract is assumed to obey the cost to carry relationship. The interest rate principally drops out of the equation. Comparing equation 19.4 and 19.5, we see that R appears in both the dm of 1 and dm of 2 terms. In the Black model, R does not appear in either the df of 1 or the df of 2 term. In fact, R appears in the Black model only in the discounting of the payoffs from the option expiration to the present. The second difference between the Merton model and the Black model concerns the interest rate term R. In the Black model, R is still assumed to be constant, but this assumption has little effect on the model's applicability to options on interest rate futures. The payoffs on the options depend largely on ND futures and ND2 futures, but the interest rate has dropped out of these terms, assuming that R is constant for the purpose of discounting the payoffs from expiration to the present. It is a small matter that is unlikely to affect the model value of the option to any significant degree. We may also use the zero coupon factor for computing the present value of the option payoff. In this case, 1 z t would replace the term x r t minus t in equation 9.5 given the following. T of f equals 1 z t t f times n d sub 1 times x in d sub 2. P is equal to 1 divided by z of t, x of n d sub 2 minus f of n d sub 2. Because of its wide applicability, accuracy in matching market prices and relative mathematical simplicity, the Black model is widely used in industry to price options on interest rate futures as well as other interest rate options. In fact, it provides an industry benchmark against which more complicated models are measured. However, we should bear in mind that the Black model, as an outgrowth of the Black-Scholes-Merton model, is a model for European option. Wow, that was a lot. Don't get caught up in the weeds in here. Just stick with the formulas. Brad Williams, Frugal Finance. Thanks for watching.